Okay, so in the last clip, we established that in a simple molecule such as ethanol, it has 3 peaks due to the 3 non-equivalent protons within the molecule. And what we established was that the more d-shielded the proton was, i.e. the closer to the electronegative atom, oxygen in this case, the further to the left-hand side of the spectrum it was. So obviously when we get the picture from the machine, we're going to have a scale on there. So as it stands now, we're just saying further to left, further to right. There is obviously a numerical scale that we need to be aware of. And as I say, there is an x-axis to the spectra. And as we alluded in the previous clip, it goes from 0 on the right-hand side, usually to 10 on the left-hand side. Now it has a name, and it's called the chemical shift. And as we said, it's kind of an analogy to the amount of de-shielding that is observed on the proton. It's called chemical shift, and it has a value between 0 and 10. The units for this are parts per million. Strange unit, but they're in units of parts per million. And sometimes you will see the symbol delta for chemical shift being given in the examples. Now, the position of the peak is given as a numerical value, and you don't need to memorize these. You will be given these in an exam, and they'll be on the back of the data sheet. But typically, values that you would generally see for a CH3 or CH2 peak, you would see typically ppms of around 1 to 2-ish, something like that. As I say, they're not hard and fast. It depends on the molecule you're looking at. The CH2 next door to that, it's slightly more de-shielded than the CH3 on the right-hand side. So this one might be observed closer to 3. As I say, there'll be a range given on the data sheet. And the OH might be seen at something in the region of 6. So you can start to look at the values now, which are given on the spectrum. And as well as now being able to calculate how many different types of proton there are, you can now start to build up a little bit more evidence as to actually the type of proton that you're going to be looking at. So the further to the right, the more alkyl chain type of proton you're going to have. The further to the left, the more alcoholic, maybe carboxylic acid type of proton you're going to have in a more electronegative environment. Now, these values aren't arbitrary necessarily, but they are relative to a sample. And in the same way that molecular masses are relative to carbon-12, there is a marker placed into the substance when you record a spectrum. And that value is arbitrarily given the value 0. And everything else then is measured from there. So it's how de-shielded a substance is compared to the sample, which is set at 0. The sample is a organic molecule. It's based around silicon, and it's got the name tetramethylsilane, and it's got a silicon atom in the middle, and it is surrounded then by 4 CH3s. It's not drawing very well. Try that again. So tetramethylsilane, it's, as I say, it's a central silicon surrounded by 4 CH3s. Now this has a number of different functions. One, it's inert, so it doesn't react with the molecule that you're actually trying to look at. And secondly, for a given amount of sample, it's actually got quite a lot of protons. So you don't need much of it